Yeah, where you were giving me some examples.
The hanging chain, the homework problem?
I don't know, you started doing something.
What did I start doing?
Started doing something with the potential energy of the chain.
Okay, so the homework problem was from the free body diagram version,
Yeah.
right? And I started doing some with the potential energy? Perfect, okay. Because yeah, we want to do it both ways. So, actually, let's go ahead. This hanging chain is actually called the catenary. That's the name of that curve. And so, quickly reviewing, you guys can correct me here. So we had an integral expression dy dx was this 1 over a integral 1 plus y prime squared dx. Was that the one we had?
Yeah.
And that's the one we assigned for homework.
No,
Notice it's up there?
what? I think the 1 over a was.
Supposed to be a y in there, right? Gotcha.
And I think the 1 over a was replaced for g times lambda.
Yeah, but that was the last step, right? 1 over a.
I don't think so. Because the way I have it was.
Let's see what you have. Oh, I didn't do the replacement yet? So we
No.
had g lambda, because there should have been a tension in there as well, right? G lambda over t. Oh, this is u. I was thinking of the Newtonian one. Okay, I'm gonna fast forward to the one with g. Okay. This was the Newtonian one, right? With the tension. Is that in your notes? Should have.
I think so. I don't have it in my notes.
Okay. Good. Now I'm oriented. Let's go ahead and try it. So yeah, we'll do a quick repeat of this thing here. So we have the potential energy. I'll just go like this. So we had the potential energy was G, Y, D, M. And that was going to be G, Y, lambda. I was just getting ahead of myself. It was going to be G, Y, lambda, DL. It was going to be G, Y, lambda, root 1 plus y prime squared dx. That was the idea. And then we got u equals g lambda integral y root 1 plus y prime squared dx. I'm going to put x prime up to x here, x1 to x2. Don't have to do it like that. That was the homework assignment, right? Okay, so the one I'm going to get to. So that was a variational problem. What we're saying is du equals 0 implies our problem. Now, I may not have shown you this yet, or did I show you guys this symbol here? The variation is the shorthand version of the entire calculation we did for the variational calculus. So that's the shorthand for it. We'll be seeing more of it. But yeah, you've got the G and the lambda. And what we already pointed out was our answer is going to be independent of G and independent of the linear mass density. That's actually a physical statement right there. So if you take this chain to the moon, it's going to have the same shape. And if you have a little thin gold chain, it'll have the same shape. as a big anchor chain. That's basically what we're talking about. Okay, good. So that was the homework problem. And what you want to do is use Euler's second form, take it through to completion, and you should find a hyperbolic cosine. Okay. How many people found that already? Some people did, some people are far away there. You can avoid that logarithmic form because the hyperbolic cosine is shows more. It's more clear what's going on. Okay, so now I'm going to get to what I just asked I had done because there's two orders to this thing. So this is an untested principle. This is why this is a question, is there really a variational principle that gives us the proper shape of the curve? So if we didn't have variational calculus yet, we'd have Newton's methods of free body diagram. And so we're going to set that one up as well and match these two, and that'll just be one of the all-time great combination of problems. So yeah, this is what we did last time. So this time, we're going to do the hanging chain. And in fact, I'm going to demonstrate it because here in my box of stuff I have a chain and some other stuff as well. Chain. This should work. So the demonstration that we're going to do this time. Make sure this is working with a nice chain here. This is what we're after. For example, if you're wearing a necklace and you take the pendant away from the necklace, so you just have the pure chain, then, when you lean forward, you've got a catenary, like I was just saying. And this is a chain here. If this were a boat anchor chain, it would also be a catenary. And the other thing, that's the shape it takes. Other people say, well, it looks like a parabola. And in fact, if you take that hyperbolic cosine and expand it to second order around the bottom, it will be parabolic. But it goes up steeper eventually. So the other point that I want to make is the bottom of this curve here is flat. And if I just change the parameters here, this 2 is the catenary, and it's the shape of the bottom of the smaller one. So that can all be shown mathematically. That's what we want to do in our problem here. Good, so that's the shape that a chain assumes under gravity. And this one here, we get an answer, but I'm not so sure it's true. This one I just did, or showed you, I want to do the free body diagram version. So now we have X and Y. It's one of those problems where you can do one first and the other first. So I came to class thinking I had done this first. Yeah, so we had that chain. In fact, why don't we just do this? Let's work off of the actual catenary just because we have it here. Okay, so say this is one of them. And go right in the middle here. Put this x-axis down here. And here's my curve. What I could do is hold this here, and if I had a scale, it would register a tension, a horizontal tension. So I'll move that out of here now. So we know there is a tension, horizontal direction. And likewise, if I had a scale here, it would register a force. So I'm going to write F. That's going to be my three-body diagram. Got X, got Y, and am I missing? Force holding that tension point over there. Somewhere in here, there's a center of mass. And there's an M times G. Remember last semester we showed that the weight acts at the center of gravity, or the center of mass. So something right there. But we can now write this down, and we get an angle. So you can see in the X direction, we have minus T plus F cos theta equals 0. And in the Y direction, we have minus mg plus F sine theta equals 0. So we can combine these two. And if we combine these two, we get tan theta. If we divide this by that, is equal to mg divided by t. And that's what I'm going to work with. So I can make some more room over here. Make some more room. And so far so good, right? Now this tangent of theta is actually the derivative of the curve at the endpoint x here. So we could say we have dy dx at that point x that I've indicated is equal to g over t, but then the mass is the integral. The mass is the integral of lambda root 1 plus y prime squared. I'm going to go ahead and write ds from 0 to x. Same thing we had before, lambda dl. So integral over dm is the mass. That's lambda dl, and there's our dl there. So now we're getting to the point I started the class off with erroneously. So now we would have g lambda over tension integral root 1 plus y prime squared ds from 0 to x. And this is going to be a homework problem as well. It's going to give us that hyperbolic cosine. But there's some other physics in here as well. Like, we don't know the tension here. In G and lambda, we can say, sure, we have those. We don't know the tension, but we can argue that the tension itself must be proportional to G and lambda. Because think of this, you've got this chain here. The scale is telling you a tension that's pulling to the side. If G increases because you're on Jupiter instead of, or G decreases because you're on the moon, then that tension is going to decrease proportionally. And ditto with lambda. If the chain is more massive, then that tension is going to increase as well. So we're going to argue that tension proportional to G and lambda both. And then in that case, on dimensional grounds, we can see that y over x is dimensionless. And the integral here, the integrand is dimensionless, but we have a length here. So this G lambda over tension, you can also check it out, but it's going to be 1 over a length. Okay. So that's where I bring in this 1 over k integral 0 to x root 1 plus y prime squared dx. You guys are gonna love this, and the combination of the one you've done already with this one makes for a really complete problem. Now you might think, wait, we have to learn to have a derivative on one side and an integral on the other. But we luck out on this one. If we take a derivative from both sides, because we have x as the upper boundary, we just get the, I'll even do it for us. And then we'll call the rest. By the way, when you write this up for homework, definitely take it from top, for your reference, take it from top. But yeah, we're gonna have b squared y bx squared is equal to 1 divided by a root 1 plus, and that y prime, remember, is dy over dx squared. This is taking the derivative of the left and the right side. So here, find y of x. You do a substitution and then you do an integration. Very nice. And remember, you're looking at the hyperbolic cosines and perhaps their inverses. So this is the convincer. We could have just as well have done this one first. And then when we did the potential energy one, this would be the one we trust, so to speak, first, because Newton. And then we'd see that we had a variational principle. So we do them both, and then what we find is that the laws of physics can be expressed in terms of variational principles. That's the takeaway from this one here. So this one is straight on, free body diagram, Newton, and the other one is a variation principle. And they're both going to get the same answer. That's important. What do you guys think? Was that the first homework problem last time, that one?
I think it's the sixth or second. The hanging chain is the second one.
What was the first one?
Some other thing. Minimal surface area.
Good, yeah. Yeah, it's hyperbolic cosines all the way down. Yeah, so that already puts together a nice set. When you do all three of these, they're all very closely related. And have some technique we did last semester, some new stuff. And then we'll take it into physics problem. I did the multivariable Euler second form, right? I did that proof. So yeah, we have all the ingredients to turn to physics now. This is how we're going to segue into physics with variation calculus. Okay, good. So yeah, you got this construction. When you work this one, definitely start with the construction. Take it through to here, then you can do a substitution, solve it, one more integral, and you're good to go. And I will put the answer here because we want to discuss it again. So you can already see where that length came in, that letter A. And so when you get this answer without arbitrary constant, A hyperbolic cosine x over A, right? You can have an integration constant here and here, so that's just the simplified version. Yeah, when you get this, then x equals 0, hyperbolic cosine of 0 is 1, right? So that's A, you're getting this here. Now you know what, just to add to the mix, this is all one good theme, you guys remember the definition? Hyperbolic cosine, I'll just write of x equals 1/2 e to the x plus e to the minus x. You guys remember that, right? So what I'll say is once you get this solution here we'll add this to the mix. Just quickly expand it to second order. So you see the parabola. Expand. Star to second order. That's easily done with some substitutions. And then you'll see that you do have a parabolic curve at the bottom. And of course it goes up steeper on the sides. Perfect. So now we have a really nice set in the variation calculus with some important results. Okay, so now we're going to turn to mechanics proper. Remember I said this was going to lead to Newton's law, this variational stuff. That's what we're going to do now. And once we have that, you can convinced. It's totally convinced. So this section is called the principle of least action. Least action. And what it says, there's this thing called the action, and it's defined as the integral of the Lagrangian with respect to time. That doesn't tell us anything. But this Lagrangian, I'll just write this terminology down for you. Has this meaning here. It's the difference of kinetic and potential energies. So if you have a mechanical system and it's doing its mechanical thing, okay, and you take the kinetic energy and subtract the potential energy from it for the entire system, then that actual motion that occurs in nature is the one for which the action takes a minimum. So principle of least action, mechanical system, so the motion of the mechanical system minimizes the action. So the actual motion, the true motion in a system minimizes the action. Used to be a conundrum philosophically. How did it know? Minimizes the action. Now what I'm going to do is just plug in a point system here, and step by step we'll show what happens, and at the end of it, Newton's law comes out. Okay? And that'll be the convincer. So consider the basic system of point masses. Remember we ended up with multiple point masses last semester. And it's going to be a conservative system, so it has a potential energy. And so here's what we have. So what we have is this Lagrangian is equal to the sum of 1/2 m sub I r sub I about squared. So individual kinetic energies, I equals 1 to n. And then we have to subtract off the big potential energy of these. And you know, if you take x, y, and z for each of these, would be 3 times n variables. We'll take it together. We did a little bit with this last semester in terms of the sum, the energy. But the thing thing is, this L is a function of the coordinates, the velocities, and under circumstances also the explicit time. This one doesn't have the explicit time, but under circumstances. So we're going to compare this to f equals f of y sub 1 to y sub n, y sub 1 prime to y sub n prime x. This is the thing we did the variational calculation on. And just by relabeling, we see that this is coordinates, velocities, and time. This was, a function is derivative in the argument. So we're just going to inherit this thing. And this one, where d over dx, df, dy sub I prime minus df, dy sub I equals 0. Here, I'll put after this f here, v equals integral f dx, dv equals 0. So this here was the variational problem we've studied so far. And the claim is that this Lagrangian business, if you minimize it variationally, you're going to get the actual motion of the system. So yeah, we've been studying this, and you have to look at this some more. But what we're going to do is just relate this to this. And what we can do is say, okay, the y's are the r's, the y primes are the r dots, and the x is the t. So we can actually inherit this. And very, very important point, in order to get this proof, we had to make sure these were all independent of each other. Remember I made that point? They have to be independent. Okay, so without further ado, we're just going to apply the Euler-Lagrange equation to this thing and see what happens. I gotta erase this. Euler-Lagrange equations. They're going to look like this. I'm just going to translate. We're going to be d over dt partial L with respect to r. I'll use j dot minus partial L with respect to r sub j equals 0. And what I'm doing here is doing 3 at a time because I have the vectors. Okay? These derivatives are 3 at a time. These are gradient substitutes, right? Yep. So here we go. Difference between the kinetic and the potential. So right under here I would have d over dt of m sub j r sub j dot, because it's a 1/2 and the 2, right? And minus this, minus, because I already have a minus, minus times minus is plus, and the dl dr sub j is just going to be du dr sub j equals 0. But this is just a gradient. When I say del u with respect to r sub j vector, that's just a gradient with respect to the j of here. So now I have m sub j r sub j second derivative plus gradient, I'll put a little j there, equals 0. Who sees it? Or m sub j rj second derivative equals minus gradient sub j cubed equals f sub j. Newton's law. What's a condenser? Well, you're going to see in time that, in fact, you're going to know this one better than you know Newton's law. This is the equation we use for a lot of things. When things get more difficult, this formalism has more coming for it. So anyway, I don't think I left a step out, basically. This was just for point particles. You guys remember this example here? One example was u of R1 and R2 minus G M1 M2 R1 minus R2 magnitude. Right, we did that one, I think it's some length last semester. The two particle potential. And this generalizes to n particles with a bit more mess. Good, yeah, so there we go. We have Newton's law from the principle of least action. If that's all we had, you could ask why. My God, we just got Newton's law, we already have Newton's law. But the form of the variational principle that we have a scalar in here means when we started having different coordinate systems, we have huge advantages to finding the proper equation of motion. So this will give us big advantages in finding equations of motion. So we got to start our way through some of the examples. Good. So that was the condenser, Newton's law, right here, Newton, and an explanation plan. And I'll leave that up. So here's the advantage to this system of operating. So this principle of least action, LET, it has a scalar in here, right? T minus U. And so, and since you're just minimizing this, it's going to be independent of the choice of coordinate systems. So you just your whole job is to construct this, no matter what coordinate system you use, as long as they're independent coordinates, then you're guaranteed to get the correct equations of motion. So the correct equations of motion here, well, I have to introduce generalized coordinates. But I'll put this here for your notes. Scalar, not the vector. So, independent coordinate system of the choice of coordinate system. Provided, of course, the coordinates themselves are independent of each other. We'll stress that repeatedly. And then you have that coordinate system, then you just have to write the equation of motion. You know, I'll actually put this down here, and then we'll work our way into it. So, let's go ahead and call this, make some moves. So there's a concept called generalized coordinates. And we're familiar with it in the sense our already. We have Cartesian coordinates, we just found about them here. What if we have plane pole, cylindrical, spherical? You guys remember how complicated the equations of motion get with spherical polar coordinates? They're a mess. Right? You can't memorize them. You don't have to. If you can just get that Lagrangian, then you're just going to apply these equations, and the correct equations will come out. So that's already a huge benefit. So we got to work our way into that step by step, but I'm going to actually put the result up for us. So if the Lagrangian can be expressed in terms of these generalized coordinates, just think plane, polar, or spherical. Can be expressed in terms of independent generalized coordinates. Generalized coordinates, that's the important terminology here. Generalized coordinates. So L is going to be L of Q1 to Qn, Q1 dot to Qn dot. So, all right, generalized coordinates Q sub I, and their derivatives. So if you're able to do this, make plane polar, then what we have is d over dt, dl dq sub j dot, minus dl dq sub j 0, j equals 1 to n. So that's what we're working towards. You see, our goal is going to be, just get that kinetic minus potential in whatever set of coordinates we have, then we automatically get the right equations of motion. Which is huge, but it's still only an equation of motion. That didn't mean we could solve it. But that'll give us those. And in fact, that's why I didn't pursue the spherical polar coordinates equation of motion all the way through the accelerations last semester. Because we don't need that, right? We'll actually get them so to speak, anytime we need it. So that's the goal, is to take a mechanical system, find the best possible set of coordinates for it, and then using the Lagrangian formalism will get the easiest, which isn't saying that much, but we'll get the easiest equation of motion from it. So that's the plan. Just gotta see how we're going to move through that. Yeah, I kind of jumped to this result here because I wanted to show us where we're headed with that. Actually, you know what? We can go, we can do two examples here. First one, suppose we're doing projectile motion. This is a problem we should always know, and we've done it 1,000 times. Is anybody doing tutoring yet? Physics tutoring? You were, right?
I am.
How about the rest of you guys? You should be able to do it. It's good for you, right? After you've seen these problems from Physics 2A for the 300th time, it kind of sinks in. But anyway, yeah, let's look at projectile motion. Will just do it in X and Y the way we've learned. We know we launch here, and there we go. What's the kinetic energy? And what's the potential energy for the projectile motion in X and Y here? So here, this Lagrangian would be 1/2 m x dot squared plus 1/2 m y dot squared. That's kinetic. What's the potential energy? mgy. So we'll subtract off minus mgy. Yeah, so there's our projectile motion Lagrangian. The equations of motion, let's just do this. So one of them is going to be d over dt, let's get practice here, dl dx dot minus dl dx equals 0. And the other one is going to be d over dt partial L with respect to y dot minus partial L with respect to y is equal to 0. And we can do these with the quickness. dl dx dot is mx dot, so we get a mx double dot. There is no explicit x in here, so that equals 0. The second one here, we're going to have my second derivative minus dl dy, so it's going to be plus mg equals 0. And what we see is that's good old free fall. Y double dot equals minus g. So they just come out automatically. Come out automatically. Projectile motion is a good example. There are other deep things lurking here that we'll get to pretty soon. And in fact, I should say something here. This one here, we actually already have a conservation law because dl dx dot is a constant, right? So I'll put here as a note. Because this was 0, dl dx dot, which is dl dx dot equals mx dot equals constant. Constancy of linear momentum in the x direction. So this one, everything just falls right in our mind. We've studied this one before. So what do you guys think is a better example for the next example? Collision problems. Those will come in later. The next Lagrangian that I wanted to talk about, I was about to do it before I remember this one, is the central force. Right? We spent a lot of time studying central force. And here we're also going to see stuff will just fall right into our lap. And that will be exactly a good place to end. So, central force Kepler problem, how could we ever forget it? So central force, and instead of going through the entire development, we'll just remember what the kinetic energy was once we were in plane polar coordinates. Remember the kinetic energy in plane polars? Half m r dot squared plus r squared p dot squared. You guys remember that, right? No?
Wait, it has been along somewhere.
It's been a long time. It's all coming back to you though, remember that? This was when we had plane polar coordinates and we took the v squared and turned it into that. Now, the central force potential, it had a built-in minus sign. We said minus alpha over r. That came from that Newton thing I had just written down a minute ago. So yeah, that's the Lagrangian. And the interesting thing is, now we got to write the equations of motion down. And so we have two of them. We have them in phi, and we have them in r. And in phi, it would be d over dt dl dp dot. We were just translating to the new set of symbols. Minus dl dp equals 0. In fact, we're going to continue with this one. Because remember, there is no phi in this Lagrangian explicit. That means that's 0. That means that's conserved. Right? The conservation laws, they just fall right into your lap in quantum mechanics. So this is 0. Therefore, cancel, MR squared phi dot. Okay, it's been a long summer. Anybody recognize this? Angular momentum. L equals constant. So the angular momentum conservation just falls right in your lap. Built in. And then this one, we would do d over dt dl dr dot minus dl dr equals 0. And then something will come out as well. So that's how we do this system of mechanics. We have to find this thing, kinetic minus potential, and then the equation of motion are just going to fall out. The conservation laws are going to be built in very close to the surface. And it's the greatest. This will be your secret weapon. If you're helping someone with a really hard problem, they'll say, wait a minute, I've got to go into the ground. You'll come back to the answer. Oh, it's easy. That'll be your strategy. In some things. Good. This is a good place to break. So we had enough homework, right? We added a couple problems. Conceivably Wednesday we could add another one, but that'll make a nice set for this week. Good.